Hello and welcome. This is a group presentation of the Voyager 2 mission to Uranus. This is for Geology of the Planets, Geoscience 120, Section 201. This is presented to you by Ellie Donath, Sierra Bahari, Rachel Johnson, Michael Mullick, and myself, Jacob Campbell. So let's jump right into it. So a little bit about the Voyager 2 mission. It was launched out of Cape Canaveral, Florida at Launch Complex 41 on August 20th, 1977. It was a flyby mission intended to pass by Jupiter, Saturn, Uranus, and Neptune, and by being a flyby mission, it meant that there were no planetary landings involved. The Voyager mission was designed to take advantage of a rare geometric arrangement of the outer planets in the late 1970s and 1980s, and this allowed for a 4-planet tour for a minimum of propellant and trip time. This layout of Jupiter, Saturn, Uranus, and Neptune, which occurs about every 175 years, allows for a spacecraft on a particular flight path to swing from one planet to the next without the need for a large onboard propulsion system. The flyby of each planet actually bends the spacecraft's flight path and increases the velocity enough to deliver it to the next destination. This is called the gravity assist technique and was first demonstrated with NASA's Mariner 10 mission to Venus and Mercury in 1973 and 1974. This allowed for the flight time all the way out to Neptune to be reduced from 30 years down to 12. So I used and downloaded a program called NASA's Eyes, which is available at NASA's website, to help kind of demonstrate the alignment of the planets that the mission capitalized on and kind of show the travel path of Voyager 2. So I'll go ahead and play that video here. You'll see Voyager 1 and 2 launch off simultaneously. Voyager 2 gets kind of slingshotted over to Saturn, gets sent over to Uranus and Neptune, and from there it gets sent off into space, kind of on this trajectory here. Voyager 2 was one of a pair of spacecraft, the other being the Voyager 1, launched to explore the planets of the outer solar system and the interplanetary environment. Each Voyager had its own major objectives at each planet. Firstly, they were meant to investigate the circulation, dynamics, structure, and composition of the planet's atmosphere, and then they were to characterize the morphology, geology, and physical state of the satellites of each planet. They also wanted them to provide improved values for the mass and size and the shape of each planet, its satellites, and any rings, and then to determine the magnetic field structure and characterize the composition and distribution of energetic trapped particles in plasma therein. The primary mission was the exploration of Jupiter and Saturn, but after making a string of discoveries there, such as active volcanoes on Jupiter's moon Io and the intricacies of Saturn's rings, the mission was extended. The Voyager 2 went on to explore Uranus and Neptune and is still the only spacecraft to have visited these outer planets. The Adventurer's current mission, the Voyager Interstellar Mission, will explore the outmost edge of the Sun's domain and beyond. So now on to a more detailed look at the Voyager 2. On the right, you'll see we have an artist's rendition of the Voyager 2 with a variety of the instruments labeled. The Voyager 2 is identical to the Voyager 1 in that they are 3-axis stabilized systems that use celestial or gyro-referenced attitude controls to maintain the pointing of the high-gain antennas toward Earth. The command computer subsystem provides sequencing and control functions. That CCS contains fixed routines such as command decoding, fault detection, corrective routines, antenna pointing information, and spacecraft sequencing information. The attitude and articulation control subsystem controls spacecraft orientation, maintains the pointing of high-gain antennas towards Earth, controls the attitude maneuvers, and positions the scan platform. Uplink communications are via S-band, which is 16 bits per second command rate, while the X-band transmitter provides downlink telemetry of 160 bits per second normally and 1.4 kilobytes per second for playback of high-rate plasma wave data. All data is transmitted from and received at the spacecraft via the 3.7 meter high gain antenna. Electrical power is supplied by 3 radioisotope thermoelectric generators. The current power levels are around 249 watts for each spacecraft, and the electrical As the electrical power decreases, power loads on the spacecraft must be turned off in order to avoid having demand exceed supply. As loads are turned off, some of the spacecraft capabilities are eliminated. When speaking about the Voyager shutting off these capabilities to save power, some of the notable ones are the imaging system, which is housed here in this camera's and spectrometer area. The wide-angle camera that is housed inside was shut off on October 10th, 1989, and the narrow-angle camera was shut off later that year, December 5th. The photopolarimeter was shut off because of degraded performance in April 3rd, 1991. The ultraviolet spectrometer was shut off on November 12th, 1998. And this planetary radio astronomy experiment was shut off to save power on February 21st, 2008. As you can see, about a third of this equipment is actually turned off now in order to save power for the Voyager 2's exploration past the planetary bodies in our solar system. So now on to a bit about what we know about Uranus as a planet. Its equatorial diameter, or if you will, the waistline of the planet, is 51,118 kilometers. That's 4 times wider than the planet Earth. Its mass is 8.68 times 10 to the 25th kilograms, making it 15 times more massive than Earth. It orbits at 2.9 billion kilometers out, or 19.8 astronomical units. And if you remember, an astronomical unit is the distance from the Sun to Earth. This effectively means that Uranus as a planet orbits 20 times further out than the planet Earth, just kind of for a sense of scale. This makes it the 7th planet from the Sun. The average effective temperature is negative 216 degrees Celsius, or 60 degrees Kelvin. The length of its day, or the time it takes to make one full rotation on the planet's axis, is 17 hours and 14 minutes. And the length of its year, or the length of one full rotation around the Sun, is roughly equivalent to 84 Earth years. Uranus has 27 moons, 13 rings, and was discovered by William Herschel on March 13, 1781. And the planet is categorized as an ice giant, which means most of its mass is comprised of a hot, dense fluid of icy materials. Water, methane, and ammonia comprise the majority of it, and it's above a small rocky core. So what did the Voyager 2 help us discover about Uranus? Well, long-range observations of the planet began on November 4th, 1985. And if you remember from our second slide, January 24th, 1986 is when Voyager 2 had its closest flyby with the planet. So for roughly 3.5 months prior to that, it was gathering all this information. In that time, the Voyager was able to discover 10 new moons, 2 new rings, gather some information about the magnetic field we'll speak about in just a moment, helped us find out that there's a boiling ocean of water 800 kilometers below the clouded surface, gathered information about the atmosphere of Uranus, which is comprised mainly of helium and hydrogen and a little bit of methane. We found out that the average temperature is 60 degrees Kelvin, or negative 216 degrees Celsius, and that wind speeds can top out at 724 kilometers per hour. It also helped to return some nice photos of Uranus and its 5 largest moons. Now, of those discoveries that Voyager 2 helped us find, we look a little bit more in depth here at the geology of Uranus. So the magnetic field that we discovered, we found that it's tilted roughly 59 degrees off axis and off center. In comparison, Earth's magnetic field is tilted about 11 degrees off the axis of rotation. Uranus has 4 magnetic poles compared to Earth's 2. For the atmosphere, as I mentioned, it is comprised mainly of helium and hydrogen, helium making up 83% of that atmosphere, hydrogen comprising 15%, and methane takes up a smaller portion, around 2%. On the surface, we find liquid hydrogen and helium, and those materials become more viscous as they approach the core of the planet. The mantle of Uranus is comprised of an ocean of ammonia, icy water, and methane. The core of Uranus is molten rock heated at 6,900 degrees Celsius with a diameter of 10,500 kilometers. And if you were to compare that to Earth's diameter, you would see that at its widest of 12,742 kilometers, Earth is actually just slightly larger than Uranus's core. Moving on to the moons of Uranus. On the picture on the right, you'll see the five largest moons of Uranus. And from order from largest to smallest as they appear in this picture, we'll see Ariel, Miranda, Titania, Oberon, and Umbriel. However, in order of actual size, we actually have Titania coming in as the largest, then Oberon, Umbriel, Ariel, and Miranda being the smallest of the five largest. Ariel is going to be the first of Uranus's moons that we take a deeper look into. It is believed to be quite young yet due to the relatively few number of impact craters we can see on its surface. The composition is believed to be roughly half water ice and half rock. It has valleys and rifts which are believed to be carved out by ammonia and methane flows, and it is the densest of Uranus's moons as well as the brightest. Miranda is the next moon we'll take a look at, and it's actually the largest, one of the five largest moons that we know the least about. Its diameter is only 480 kilometers, to kind of give you an idea of how small this moon actually is. The image on the left was taken by Voyager 2, and the photo on the right helped to reveal that those dark stripes that we see on the Voyager 2 image are actually valleys on the moon. Titania, which is not to be confused with Titan, which is the largest moon of Saturn, is similar in composition to Ariel, so that means half water ice, half rock, roughly, although it's much larger. The presence of faults on the surface indicate that Titania could have been geologically active at some point long ago, and one theory is that the surface of the moon cooled before the interior, resulting in cracks along the outside as the interior expanded. As with most of Uranus's moons, Oberon is also estimated to be half water ice and half rock. It orbits furthest from Uranus. It's heavily cratered, so we believe obviously it is a older body. And there are some fault lines along the southern half of the moon, so that indicates possible geologic activity since its formation. Interestingly, observers have found dark unknown material covering some of the moon, visible in both of these images, as you'll see here, and a few spots here and here. And it's believed that it's possible that dirty water is actually leaking from the center of the moon and freezing in those craters. And finally, we have Umbriel, which is the darkest of the major moons. It's mostly featureless as far as we can tell because it is so dark, with the exception of this known bright spot at this northern pole. It's visible as a white ring in the picture. It, it is unknown what makes this moon so dark, but it reflects only about half as much light as Ariel. So astronomers believe that this limited lightly colored spot up top is due to an impactor that had brought reflective or lighter materials with them. As for the other 22 smaller satellites orbiting Uranus, it wasn't until the Voyager 2 mission that we actually knew about any of them. If you remember, we mentioned that the Voyager 2 mission helped discover 10 new moons, and prior to the Voyager 2's mission, Uranus was thought to only have 5 moons. On the right, you'll see we have Ophelia and Cordelia. And these moons, as we move further from Uranus, the moons become increasingly dense. It is believed that the most distant moons have a silicate core as well as an icy surface, which is common to the Uranus system. However, as you come back closer toward the planet, we start to see a trend in increased geologic activity and geologic features on the moons. There are also 13 rings which surround Uranus. The inner ones tend to be narrow and gray. However, there are two on the very outer ridge that are brightly colored. One is red and one is blue. Most of them are very thin and fairly opaque and comprised mainly of large particles of ice and dust, and they are thought to be relatively new features. So what do we have left to discover about the planet of Uranus? Well, the answer is actually quite a lot. So if we could figure out more about the planet's basic composition and interior structures, it would help fill an important gap in our knowledge about how the solar system formed. Along with other exoplanets we've discovered, worlds weighing the same as Uranus and Neptune appear more common than gas giants like Jupiter and Saturn. Yet ice giants seem to require a very specific set of conditions to form during the birth of a solar system, so it'd be nice to figure out more in that field. There are already future missions envisioned for exploration to Neptune and Uranus, where detachable probes would be sent hurling into the ice giant's atmosphere. The main spacecraft would hover around in orbit for roughly 2 to 3 years and be nuclear powered. The basic set of proposed scientific instruments include a camera, a magnetometer, and a Doppler imager. Amy Simon, who is a senior scientist at NASA's Goddard Space Flight Center, says that the Doppler imager was a particularly innovative example of how the planet's interior structure could be revealed. And she says that essentially the idea behind it is that you're looking for seismic waves on the planet and that you want to see the planet begin to oscillate. And the idea behind that is similar to the studies they've done on the sun, where you can see the sun oscillating and that helps you determine its interior structure. So that about sums up our presentation on the Voyager 2 mission to Uranus. As you can see, we've still got a lot to learn about Uranus, but we hope we've provided you with some useful information and that you enjoyed our presentation. The references will be available with our PowerPoint submission if you wish to look into them further. Thank you.